Hello. In this lecture, we're going to briefly talk about inverse functions. And this lecture will lead up to the relation between exponential functions and logarithmic functions. So let's begin with the definition. So a function g is said to be the inverse of a function f if the composition of f with g is equal to x for all x in the domain of g. And similarly, that g composed with f is equal to x for all x in the domain of f. In this case, we're going to use the notation f superscript minus 1 to indicate that f superscript inverse, get my words mixed up. F superscript minus 1 is going to be the notation used to indicate the inverse of f. Now, you should have a picture in mind that if we have some domain of FA and some codomain B, and F maps A to B, then if we pick any element over here, say maybe A, little a, then little a is going to be mapped over here to say B or something, little b. So then F inverse is going to bring back those elements. So for example, F inverse evaluated at B is going to bring you back to A. Okay. And you can see that from the definition, right? F inverse of f of A better equal A. F of f inverse of A, would be B, right? Now it should be clear that in this case, they're inverses of each other, right? So F and F inverse are inverses of each other. Okay. So in particular, if G is the inverse of F, then F is the inverse of G as well. Okay. So let's go ahead and look at an example here. Say maybe f of x equals to 2x cubed minus 1, and g of x equal to the cube root of x plus 1 over 2 are inverses of each other. Okay, so if these are inverses of each other, they better satisfy this definition. If we compose this function with that, we better get back x. If we compose this function with that function, we better get back x. So just to verify this claim, let's look at f of g of x. So f composed with g. We better get back x. So what does this look like? This is 2 times g cubed minus 1. So what does g look like? It looks like that. So it's the cube root of x plus 1 over 2. The cube of the cube root is just the inside, so we're going to have 2 times x plus 1 over 2, all minus 1. So then we see that 2 divided by 2 is just 1, x plus 1 minus 1. It does indeed equal x. So yeah, f composed of g equals x. I suppose that we can also verify that f is the inverse of g. So we can say maybe g evaluated at f of x. What does that look like? Well, it's equal to the cube root of, so what goes inside 2x cubed minus 1 plus 1 all over 2. Right, so what does this become? So we have 2x cubed minus 1 plus 1. So this would be the cube root of 2x cubed over 2, which is the cube root of x cubed, which is just x. All right, so yeah, that's just verifying that f and g are indeed inverses of each other. Okay, so now let's go ahead and write down what's known as the existence theorem. Okay. Existence theorem. Okay. So there's 2 parts to this theorem, and it says part 1. So a function has an inverse if and only if f is 1 to 1, or not f, if it is 1 to 1. Okay. So recall, you might have forgotten the definition of being 1 to 1. So recall that 1 to 1 is the same thing as saying that x1 not equal to x2 implies that f of x1 is not equal to f of x2. Right, so if your inputs are different, then your outputs are different, which means that there's no repetition in the range of the function, right? If you put in this number and you put in a different number, they're not going to map to the same thing. So think of like linear functions, right? Quadratics would not be 1 to 1 because they'd be 2 outputs that get the same, 2 different inputs that have the same output. So that would not be 1 to 1. So why would this part of the theorem make sense? What's so special about 1 to 1? Well, recall that the definition of a function is that each element in the domain gets mapped to exactly one thing in the codomain. So the function takes input to exactly one output. It doesn't take input and split into 2 outputs. So if we're looking at a function f mapping over here, right? If it wasn't 1 to 1, then there would be some point over here that had 2 different things mapped to it. So if we look at the inverse, that value would then be sent to 2 different things, which wouldn't be a function. We're not going to write the proof of this, but there is that intuition that I just mentioned. And then part 2, if f is strictly increasing, how did I misspell that? Or strictly decreasing, so let's put that in parentheses, or decreasing, then it has an inverse. So why would that be the case? Well, if it's strictly increasing or strictly decreasing, then the function is necessarily one-to-one, because as you input more and more values from the domain, you're never going to stay the same and you're never going to repeat. It's going to be one-to-one, which by part one of this theorem means that it's going to have an inverse. Okay, so this is just a quick way to test whether or not a function has an inverse. And again, I should probably emphasize that this is relative to the domain that you choose for your function. So for example, the quadratic over all reals, the parabola x squared over all reals is not one-to-one and would not have an inverse. But if you limit the domain to just 0 to infinity, then that would have an inverse. Okay. Okay, so let's go ahead and maybe find an inverse, right? So suppose we're given a function and we want to find an inverse. So maybe find the inverse of f of x equals to the square root of maybe, which example do I have? 2x minus 3. If it's this. Okay. So first of all, this function here is strictly increasing. This is a monotone increasing function. As you get larger and larger x, this becomes larger and larger. So it does exist by this theorem. So now we need to find it. So the solution, you can say something like f inverse exists since f is strictly increasing. Okay, so now we need to find it. Now, in algebra textbooks and even in this calculus book, they have this like kind of counterintuitive collection of steps to find the inverse. Let's just ignore that and let's think about what we want. So what do we want? We want f inverse of f of x to equal x, and f of f inverse of x equal x. That's what we want. We know that it exists, we need to find it. So in particular, we know that, so maybe I can say like so, we want x equals to f evaluated at f inverse of x. But what is this composition here? It's the square root of 2 times f inverse of x minus 3. So now look at what we have. We have x equals that, and that's the thing we're trying to solve for. We're trying to solve for that function. So if we square both sides of this equation, we get x squared is equal to 2 times f inverse of x minus 3. If you add 3 to both sides and divide by 2, you get that f inverse of x is equal to x squared plus 3 over 2. And you can verify that that is the inverse now. You compose that with that, you're going to get back x. And if you can just visualize it, but like mentally look at it, if this composed with this, then we get that all squared, which is just 2x minus 3 plus 3, which is just 2x all divided by 2, gives you back x. So that is indeed the inverse. Okay. So, okay, we have 2 theorems to state now. So hopefully I didn't move too fast on this right here. This is kind of the heart of what, not the heart, this is the type of question you might be asked to verify, right? Know what it means to have an inverse. When does that happen? And then use a definition to find the inverse. Okay. Now, with relation to calculus now, because this is really just a recap of algebra, with relation to calculus, I need to write down theorems. So, theorem. So, let f be continuous excuse me, looking at the wrong thing. Let f have a inverse on the interval I. Okay, so f has an inverse on the interval I, and I is the domain of f, or a domain where it has an inverse. Okay, so part 1, if f is continuous on I, then so is its inverse. Actually, not, I misspoke. Then f inverse is also continuous on the image of I. So look at the image of I, you have some values, then f inverse is continuous on that. Okay. Part 2. This is kind of more of an exercise. If f is strictly increasing or decreasing, and so is f inverse. Again, this is with respect to the domain of the inverse function, which should be the range of the original function. Okay. Okay, so I think that this will be the end for this video. This is really just a recap of inverse functions and We're going to need these definitions in order to look at the exponential functions, which we will treat as the inverse of the logarithmic functions. Thank you for watching.